Swayam Prabha. Digital India. Educated India.
Having defined these quantities, the second moment of inertia and the product of inertia, we now describe a relationship between the second moment of an area about a set of axes passing through the centroid of the body and another set xy axis which are parallel to those passing through the centroid. Thus, suppose I have an area with the centroid with respect to a given set of axes x and y with origin at O, such that the coordinates of its centroid are x0 and y0. Let us choose another set of parallel axes x prime and y prime passing through the centroid. X prime is parallel to x and y prime is parallel to y, and we want to now show that Ixx and Ix prime x prime are related by a very simple theorem, and so are the other moments. Thus, Ixx is equal to y square dA. So, suppose I have a small area dA here, this is y, which is also equal to y is equal to y prime, where y prime is the y coordinate of the same area with respect to x prime and y prime axis, plus y0 square dA, and this is equal to y prime square dA plus y0 square dA plus 2 y0 integral y prime dA. Notice that y prime square dA is the Ix prime x prime, that is the second moment of inertia about the x axis passing through the centroid, and y prime dA is nothing but area times the y coordinate in the centroid frame. So, this is going to be 0. If I calculate the centroid with the origin at the centroid, the coordinates of the centroid are going to come to 0, and therefore, I see that Ixx is equal to y prime square dA, that is Ix prime x prime plus y0 square times the entire area. This way, if I know the second moment of inertia of a body about an axis passing through its centroid, I can easily calculate the second moment of inertia of the same body with respect to an axis which is parallel to the first axis but displaced by amount y0. In the same manner, we can now calculate Iyy, which is equal to integral x square dA, which I can write as x prime plus x0 square dA. Let me for convenience show in the picture again what we are talking about. This is the body, this is the centroid set of axes x prime y prime, this is x y O, this is x0, this is y0. So, if I choose an area here, this is x and this is x prime. So, x is x prime plus x naught. So, this can be written as equal to integral x prime square dA plus x0 square integral dA plus 2 x0 x prime dA. This again by the same logic as we applied earlier, that this is the x coordinate of the centroid in the coordinate system which has its origin at the centroid itself. So this is 0. So I get I y y is equal to I y prime plus x naught square a. So it is as if the entire area is concentrated at the centroid plus whatever the second moment of area is about the axis passing through the centroid. Next, let's calculate the product of area, again making these axes x prime, y prime, x, y, o, and I take an area here. The product is I x y, which is equal to integral x y dA, and I substitute for x and y as x prime plus x 0, y prime plus y 0 dA, which comes out to be x prime y prime dA plus x 0 integral y prime dA plus y 0 integral x prime dA plus x 0 y 0 dA. Again, by the arguments that we have used earlier, these two terms drop to 0, and therefore I x y is equal to I x prime y prime plus x naught y naught times the whole area. So what we have learnt is, if we know the second moment of inertia and the product of inertia about a set of axes passing through the centroid, I can calculate about any other set of axes which are parallel to those passing through the centroid. Let us summarize these. So for an area whose second moment and product of area are known about the axis passing through the centroid, I have in general I x x equals I x prime plus y 0 square times the area, where y 0 is the coordinate of the centroid, y coordinate of the centroid, I y y is equal to I y prime plus x 0 square times the full area, and I x y equals I x prime y prime plus x 0 y 0 times the entire area. These are known as transfer theorems. Using these, I can transfer the moment of area or the product of area from one coordinate system to another. As an example of the application of the transfer theorem, let us take the case of an ellipse with its length being 2a and this being 2b, with its centroid at point x 0 y 0, and calculate its moment of area, second moment of area, and product of area with respect to the xy axis shown here. So by transfer theorems, I have I x x equals I x prime plus y naught square times the area of the ellipse. I y y similarly is I y prime plus x naught square times the area of the ellipse, and I x y is equal to I x prime y prime plus x 0 y 0 times the area of the ellipse, where I x prime is the second moment of area with respect to the x prime axis parallel to the x axis passing through the centroid. I y prime is the second moment of area with respect to the y prime axis parallel to the y axis and passing through the centroid. Previously we have calculated I x x as pi over 16 times a b cubed for a quarter of an ellipse like this. So for the full ellipse, and this I left as an exercise for you there, this is going to be 4 times as much. So this is going to be pi over 16 a b cubed, which is pi over 4 a b cubed. Similarly, I y prime for the ellipse is going to be 4 times pi over 16 a cubed b, which is pi over 4 a cubed b, and I x prime y prime is 0. Therefore, for this ellipse, we will have I x x as pi by 4 a b cubed, which is the second moment of area about the x prime axis passing through the centroid, plus y0 square times pi ab, where pi ab is the area of the ellipse. I y is going to be pi over 4 a cubed b plus x0 square pi ab, and I xy is going to be 0, which is the I x prime y prime. By symmetry, it is 0 for axis passing through the centroid, plus x0 y0 pi ab. So using transfer theorems, we could calculate the second moment of area and the product of area when it was given about the centroid.